speaker and come to the end now of this session with Dr. Pereira. And Dr. Pereira holds a PhD in remote sensing and photogrammetry, which he got from the Technical University in Dresden in Germany, I think last year, if I'm right. And he will talk about his work on processing laser points, airborne laser points for 3D city modeling. Dr. Pereira, please.
Thank you very much, Professor Han. And good evening, and you all are welcome to my presentation, and it's about efficient 3D city modeling from airborne laser scanning point clouds. This is the outline that I'd like to follow for this presentation. Basically, 3D building models are widely being used for many applications such as urban planning, virtual reality, civilian and military emergency response, robotic navigation, and so on. Currently, 3-point clouds acquired by the airborne laser scanners are mainly used for the reconstruction purposes because point clouds have more automation potential than image data. Although many reconstruction approaches have been developed, reconstruction of geometrically and topologically correct 3D building model is still a challenge. This is mainly because of the scene complexities, problem of data such as data gaps and resolution issues, and the limitation of the method such as lack of model libraries. Therefore, the objective of this study is to develop new reconstruction algorithm for the reconstruction of geometrically and topologically correct 3D building models from airborne laser scanner point clouds. To achieve the objective, we introduce a new concept which manipulates the roof boundaries efficiently than ever. Actually, we work with the raw point clouds, as you can see, or maybe I can use a pointer. The first step of our approach is the roof plane extraction. Actually, we achieved this via 3 sub-steps. So our steps begins with segmenting the point clouds into planar faces. As you can see, we obtain different planes, different faces. As you can see, these faces are, the segments are appeared in different colors. And then this is followed by a classification approach which this classifies the planar segments into terrain and off-terrain segments. As you can see, those two classes are appeared in red and green colors. So from the classified off-terrain segments, then protection roof planes are extracted by applying different constraints. Having protection roof planes, the next step is to extract the roof boundaries together with the relationship between roof planes. Since we are working with the point clouds captured by the airborne laser scanners, that is, airborne laser scanners view the top view. So for the reconstruction schemes, we have to rely on the rooftops. As you can see in this figure, the complex buildings may contain with more than one roof planes, and different planes are shown in different colors. So the inner boundaries of these planes are demarcated by the ridge lines and also the step edges. So for this study, we use the term feature lines to indicate step edges and the ridge lines. On the other hand, these feature lines describe the relationships, topological relationships among those roof planes. Therefore, we first extract the ridge lines by intersecting adjacent roof planes, while the step edges are recognized by analyzing the boundary points located along the common borders. Once we extract a ridge line, we store the relationship between these in between roof planes via graph edge. According to the graph theory, any graph G can be defined with a set of vertices V and edges E. For example, for this building, if we extract the ridge line in between roof plane 2 and roof plane 3, so at the same time we create a graph edge together with two nodes. These two nodes are indicated the corresponding roof planes. Similarly, with the extraction of another ridge line or a step edge, we can create the graph edge, as you can see. Finally, we obtain a complete graph, and we call this graph as roof topology graph because this graph describes the entire roof topology of this building. So the next step is to reconstruct the 3D building models based on the acquired graphs. Actually, we believe that any 3D building model can be reconstructed by fixing the vertices where the edges meet. As you can see, for a building, we come across two types of vertices. These are the inner vertices and the outer vertices. When we analyze the roof topology graph together with the rooftops, this shows that a shorter cycle available in a roof topology graph always corresponds to a certain roof corner. Therefore, we extract the shorter cycles available in the roof topology graph using the famous Ridge-Class algorithm. For example, if we extract the shortest cycle having nodes 2, 4, 3, 2, then at the same time we are able to recall the corresponding ridge lines from our database. Once we know the ridge lines supposed to converge, then we are able to reconstruct this inner vertex. Similarly, with the extraction of another shorter cycle, we are able to reconstruct another vertex. Similarly, the same procedure can be followed for the reconstruction of all the inner vertices. Okay, it's also possible to extract outermost cycle, and this is the outermost cycle in this roof topology graph, and we can extract the outermost cycle by removing the inner edges. It is clear that with the forward traversing along the outermost cycle, this leads to incorporate all the outer vertices. As you can see, for example, if we travel from this node to the adjacent node, then we can recognize this ridge line and these two outer boundary line segments that are going to converge. While by knowing all those corresponding the boundary line segments, we are able to reconstruct this vertex. Similarly, other vertices can also be reconstructed. So this is our procedure. So finally, we obtain the 3D rooftops. So these are the rooftop, and by projecting the outer vertices until the ground height, we can reconstruct the wall segments. By combining these two, we are able to obtain complete 3D building model. And this figure tells that our algorithms are capable to reconstruct the dormer structures as well. Okay, and these are some selected sample results, sample roof models that have been developed by our algorithms, and these results tells that our algorithms are capable to reconstruct multi-layered oblique roof planes, and also different roof components having oriented into different directions, and also these are the flat roof buildings. Flat roof buildings having multi-layer height jumps, and this is still a challenge for many other reconstruction approaches. Okay, so to test the performance of our algorithm, we have chosen 3 test sites in the Fahingen city in Germany. Actually, these test sites represent the historic part of the Fahingen city and some multi-storage buildings and some rural areas. So these are the final results, final 3D city models that have been reconstructed from our algorithms, and so you get a nice result. So you can see nice results. So we believe we can reconstruct different type of buildings very well. Okay, so our experiments further tells that our algorithms are able to maintain the gutter symmetries. Actually, we obtained the 5 centimeter gutter symmetry in between two opposite gutters in a gable roof, and also this figure tells that our algorithm is able to maintain the gutter alignment along the gutters, and this is a result of the roof heights. And since I'm running out of time, I'm just moving faster. So this is the overall evaluation, and this table tells that we obtain over 90% correctness, but how we obtain little less completeness. This is not a failure of our graph-based reconstruction approach. Actually, this is due to the defect of the classification step, which we introduced very earlier. As you can see in this figure, some buildings were completely misclassified into terrain. Therefore, our algorithms were not able to extract these roof planes. So this is the reason to reduce the completeness. Actually, we obtained very good planimetric and height accuracy, as you can see. Actually, we took part with the ISPRS building test project, and we obtained the second highest results among the 17 participants. So I would like to conclude that our graph-based 3D building model reconstruction approach is highly capable for reconstructing different complex building structures, and our algorithms are capable of maintaining the gutter symmetries, and also flat roof buildings having multi-layer height jumps can also be reconstructed very well, and this is still a challenge for many other methods. And also we noticed that we should improve the classification step, and further improvements in terms of the planimetric accuracy, since we obtain little less planimetric accuracy, can be obtained by integrating the image data. And happy to say that we already implemented that part and obtained the best results among the 17 participants who took part in the ISPRS data. Okay, thank you very much.
Thank you very much, Dr. Pereira, for this very interesting talk and very groundwork. The completeness might be not perfect for your results, but at least for the work, it's very complete.
Thank you
very much. Yeah, I think we should not have many questions anymore at this time. If somebody has a very urgent question, yes, please.
Point that is the region you have selected 11 nodes, 10 to 10 11 regions, and somewhere in mid, so you have one some point you have selected. So when you yes, there.
You mean this figure?
Yeah, exactly.
Yes.
So how did you select that particular point? Now, do you have any sort of methodology to select that?
Actually, we used this is the outermost cycle in the roof topology graph. If you see this figure, this is the complete roof topology graph, and by removing these the inner edges, you can get the outermost cycle. With the forward traversing along the outer cycle, we can incorporate the outer vertices, that is these ridge lines, and these two outer boundary line segments, not the inner points, not the inner vertices. May I answer well?
Okay. Any chance for you to apply your method also to data in Sri Lanka?
The problem in Sri Lanka is still, actually, as far as I know, in 2005, some people have collected the airborne analysis scanner data along the coastline, but still we don't have any other details, especially the Colombo area. So actually, we can apply our algorithms anywhere in the world, but for Sri Lanka, the thing is, we don't have, nobody have collected the data yet, and I think very recently people are going to collect.
Okay, so thank you again.
Okay.